Thank you, Serge. And now it is my great pleasure to introduce the conference keynote presentation. And I'd like to welcome Maria Girone. She graduated from the University of Bari in Italy, where she received her PhD in high-energy physics. In 2002, she joined the IT department at Cern as an applied scientist and staff member. Then she became deputy group leader of the Cern IT experiment support group. In 2012, Maria became the founding chair of the worldwide LHC computing grid operations coordination team and was responsible for the co-operations. In 2014, she was appointed the computing coordinator for the CMS experiment at Cern. And later, Girone joined the management of the team of Cern openlab, taking over the position of CTO as of January 2016. So looking back on this long career in IT in support of high-energy physics, it's a great pleasure for us to welcome a leader of applying computing to solving some of the most challenging problems in high-energy physics, understanding the nature of mass, and leading one of the largest scientific experiments in the world. Welcome, Maria.
Good morning, everyone, and many thanks for the opportunity to be here today. I would like to share with you what we do at Cern and what is going to come for the future in terms of challenges in computing over the next decade. And I'm also going to cover what we think is going to be the role of technology to help us tackling some of these challenges together. I'll give a brief introduction of Cern, its complex of accelerators. I will then present to you what the experiments are made of and how we built and operate them, what are the data that we collect at Cern, and how we store them at Cern and actually worldwide on the grid. I will then talk about the upgrade program of the Large Hadron Collider and the computing challenges that are linked to this. And then I will move to the way in which we are looking at solutions about these computing challenges, in particular in the areas of data center technologies, computer performance and software, and of course, new techniques like artificial intelligence and machine learning, deep learning, that are already under investigation and are going to help us in order to face in a complete way these challenges in the future. I will then have a couple of slides on how we work with other sciences and about knowledge transfer. So, just a brief introduction about Cern. Cern is the world's largest European laboratory for particle physics. It was created just after the Second World War ended in order to give nations the opportunity to come together and work together for science for peace. It was a very important moment to do this, in particular in Europe. And you can see actually some images about those times, in particular the time of the Amsterdam meeting in 1953 when the convention was signed, and also the first moments of the groundbreaking in the Meran site in Switzerland near Geneva, where Cern is hosted. Today, the Cern site, this Meran site, looks like this from an aerial view with the globe that has become the symbol of Cern. but is actually a larger complex, as it contains also not only the sites where we have our offices and some of our infrastructures, but also the complex of accelerators that you can see from this aerial view. Compared to the airport that you can also see at the bottom of this aerial view, we are really talking about fairly large installations and infrastructures. This, the laboratory really has a very nice location because it straddles the Franco-Swiss border near Geneva and basically occupies this area between the Lake Léman and the Jura Mountains, which actually give us challenges in order to relax over the weekends when we can. The two sites are one located in Switzerland and the other one is located in France. Just an overview of who are our members. We had 12 founding members at the beginning of this journey, which signed the conventions in 1953. But today we count on 22 member states, a number of associates and observers, which really makes CERN a worldwide endeavor. We have a budget of approximately 1 billion Swiss francs per year. And we support a very large community in higher engineering physics of about 15,000 people who are located all over the world. So scientists, when they come at CERN, they want to answer the fundamental questions that we have in particular in our field. So we really want to probe with our instruments the fundamental structure of the universe, and by using accelerators we can recreate the conditions of the first instance when the universe was born, and give some insights about fundamental questions like why we have a very important asymmetry between matter and antimatter, and shed light on the existence of dark matter in general, how our universe is made. But CERN is not only fundamental research. Very importantly, actually, we also are leaders in developing new technologies in many different sectors, from accelerators to detectors, information technology, and I would like to mention that the web was born at CERN in 1989, and we have a very important spin-off that I will cover very briefly at the end of the talk. In particular, given our expertise, medicine is certainly one of the spin-offs which are more important for society, so I would like to mention this here. A pillar of what we do is also the training and the education of young scientists. This is very important for CERN, and we have a very solid program dedicated to students. But what really makes CERN a very, very important and a special place where to work is its capability of uniting people from different countries, from different cultures, all under the purpose of advancing the frontiers of knowledge for the benefit of all. And this is really a very special added value that we can have in a laboratory like CERN. Moving on to the complex of accelerators, CERN has got a unique set of accelerators. They all have their physics program. And I would say that today, probably the most famous and the largest and the most powerful of all is the Large Hadron Collider. So this is where we are going to concentrate on for the rest of the talk. And you can see here an image of the tunnel with actually the superconducting solenoids, which are in blue, which are a few thousands. Again, from the view from before, you can see that we have actually a a set of accelerators which are boosting the energy of the beams and injecting to the next accelerator up to the last ring of the chain, which is the LHC collider. There are 4 interactions points at this collider, and these are the 4 main experiments that are built in order to understand the products of these collisions. And it is actually built for financial reasons, underground, about approximately 100 meters underground, has got a circumference of 27 kilometers. So it's a big apparatus, probably the biggest in the scientific field that so far has been created. The particles are accelerated very close to the speed of light. And just to give you an idea, they can complete in a second more than 11,000 turns, which makes actually the LHC certainly the fastest racetrack that we have on the planet, but is also the place where the most powerful magnets and the most sophisticated detectors are built. It contains a pure vacuum than the one in outer space, and actually also contains the, when the beams are colliding, the hottest spots in our galaxy in very, very tiny space. And we can reach spots which are millions and millions times hotter than the center of the sun temperatures. But because we have also superconducting magnets, we also have to actually cool them down to very close to the absolute zero, to minus 271 Celsius, which makes actually Cern, in my opinion, one of the coolest places on Earth where to work. So what comes next, and actually a comparison of the kind of time scales of the accelerators and their life is given by this this graphic. You can see the LHC, which is running in operation right now. Design studies started as early as 1985, when basically the previous collider, the lab collider, was starting to be constructed. So this is a very long journey for complex machines such as the accelerators. The construction of the next phase of the Large Hadron Collider, the so-called high luminosity LHC, just started a few weeks ago, and the operation will take us up to 2035. So typically a collider lives for decades. And we have a program with the LHC, which is going to last for additional 20 years. So we are really at the beginning of a journey. But because it takes time to think, to design, and to construct new accelerators, we are also thinking of the next generation of colliders. We have started some investigations and studies of the future collider, circular collider of Cern, which would be located in a very nice area between mountains, so between the Jura and the Salève mountains near the area of Geneva. Cannot be much larger as to just fit in that space. And you can see the LHC would be serving as an injector to this new collider, which would be approximately 100 kilometers of circumference. It would go also under the Lake Léman. So that's for the future. Now, getting back to the reality of today, I would like to spend a moment to describe the experiments. These are really masterpieces of technologies. I'm always very happy to look at this picture. It's a great picture of the experiment where I've been working as a computing coordinator. I'm still working in it. It's a section of the CMS experiment. And what these, the way to picture these experiments is really to think that they are like gigantic cameras which are built in cathedral-sized caverns. And in fact, the dimensions are very, very impressive. You can see the schematic of the largest of these experiments at the Large Hadron Collider, the ATLAS experiment, compared to some humans which are standing at the bottom and on the side. You can see that these are very, very complex apparata. The experiments, because they are so big, are really run by thousands of members of the collaborations. They're coming from institutes from all over the world, which basically means that we not only have a technology challenge here, but we also have a social engineering one. And it is complex to be, for instance, coordinator of a collaboration of a few thousand physicists who want to analyze data. So there are a lot of challenges in operating these experiments and being in these collaborations as well. Now, another important aspect which is surprising often people is that each of these institutes which participate in a program like an experiment at the LHC actually has the responsibility of building parts of the detectors in their own laboratory. And then these parts get assembled at Cern. And when we started the journey of the LHC, I can assure you, we've been putting together all these different components, and we have turned on these large detectors, and they were functional from day one. And this is a major success for such a complex a system as the one of the experiments in high-energy physics. Going for some impressive numbers, at least impressive to me, ATLAS is about 50 meters long, is about 25 meters high, weighs as much as the Eiffel Tower, and its counterpart experiment, CMS, is twice as small as ATLAS, but is twice as heavy. So no matter why the C of the CMS experiment stands for compact. It also contains the most powerful superconducting solenoid that has ever been in its kind, and the stored energy of this solenoid would be able to melt approximately 18 tons of gold. Now, these two experiments are the so-called general purpose experiments, so they're able to investigate large spectrum of physics, and they have been built and designed independently with very independent detectors, which makes it possible that discoveries can be cross-confirmed. And this is exactly what happened in July 2012 when Cern announced the discovery and the confirmation of the existence of the Higgs boson. The other two detectors are equally important. They have more specific programs in physics, a little bit smaller in size, and the collaboration is also a bit smaller, but still impressive. The ALICE experiment is dedicated to the study of the quark gluon plasma. This is a state of matter which existed just a few moments after the Big Bang. And the LHC-B experiment, the B is standing for being dedicated to study the behavior difference between the B quark and the anti-B quark to explain again, the asymmetry that is noticed in the universe between matter and antimatter. Now moving to the kind of data that we collect. This is a schematic, and actually it's called, we call them event displays, of what happens during after a collision of a proton and another proton. Particles are created, and then they can decay into even more particles. So events are rather complex in their final state. And at the LHC, we have something like up to about 1 billion particle collisions that can take place every second. So it's an impressive number. Not all are interesting to us. Not all processes are processes that we want to study. Some are already known. So there is a very impressive data mining problem at the LHC in order actually to be able to anti-select what we know and we don't want to know more, and actually be able to select only those interesting, potentially interesting candidates that we want to study. And as the rate at which the data is generated at the LHC is impressive, and we have data generated something like 40 million times per second. This is the rate at which the beams are crossing. We can't store all this data. Would be storing petabytes a second, so really not what we can do. So we had to put in place a number of important and smart filters, which we call triggers, which make it possible that we further reduce this enormous quantity of data to sizes and dimensions and samples that we can then afford to analyze and study further. The first selection is happening with the hardware, using hardware, and we go down to something like 100,000 selections per second, so we have reduced by factor 10 to the 4. And again, we have another reduction of 10 to the 3. And we bring down the terabytes per second of the hardware filters to the gigabyte a second after having applied software filters. Now, the important thing of this step is not only that we are doing smart selections, and we can't be wrong in this, otherwise we might be missing physics, so it's always a very delicate process, but also actually that we end up in having a complex data mining problem that has allowed us to reduce by 1 million and take decisions within hundreds of milliseconds. And this is really very, very important factor to keep in mind, especially for the future. What do we do with this data? We store it first place, certainly, in the Cern data center. So I would like to spend a couple of minutes describing you what we have in terms of infrastructures at Cern. This is the view from above of our data center. And we collect about 30 to 50 petabytes per year, per experiment. So Cern is handling a number of hundreds of petabytes to process and store per year. We could not host all the needed infrastructure in the Cern site of Meran, so we chose a remote infrastructure. This is at Wegener, in the Wegener Center in Hungary, in Budapest. The two centers are connected via 300 gigabit per second links, which is shown in the picture. And in total, between the two sites, between the Meran site and the Wegener site, we have something like 400,000 processor cores and about half an exabyte of storage between disk and tape. You can see also a picture of the Wegener data center on the right-hand side. And actually, the two centers operate virtually as one. The data, which is collected at Cern and then gets also stored with the primary copy on the site, has to be accessed by many physicists around the world. And as I said, each experiment produces between 30 to 50 petabytes annually that needs to be studied, and data analysis has to be run. This schematic is showing the entire data processing chain that we have in an experiment in high-energy physics. From when the data is collected, you can see the detector up there. We talked about the fact that we generate data at rates of about 40 million times per second, so 40 megahertz. And then we have this white box that explained this already, the hardware and the software triggers that we apply. And as the decision-making process happens within milliseconds, we call this online. So we do this basically in real time. At the end of this real time, a set of operations allows us to ensemble the data at a throughput of gigabytes per second, and we have the so-called primary raw data that is then collected and stored permanently at Cern, and another copy on the grid. But this is not the data that we actually can give to the analysts in order to be studied, because this is containing only the electronic signals which are coming from the millions of meteor cables which are placed at the detectors. So what we need to do is to run complex algorithms, which are called reconstruction algorithms, given the input of the conditions at which the experiments in that moment was producing the data. And then we have the so-called reconstructed data. We then need to compare, we are not done, we need to compare this data that has been produced at the, and read out through the experiments. We need to compare this real data to simulations, to what the theory predicts, in order to be able to then compare what is foreseen by the theory with what we observe in reality, and make discoveries or make precise measurements. And I'm getting back later during the talk between these two tasks, which are very important tasks, the reconstruction and the simulation. This is why I wanted to spend a moment to talk about what they are. Now, the data is then has to be made available to the world. Physicists are located, these 15,000 people are not sitting at Cern all the time. And the way in which we have made this possible is through the worldwide LHC computing grid. Is an international infrastructure which really combines the storage resources that we have into a single, a coherent infrastructure which is accessible by everybody. Is quite hierarchical, not only in the way in which it's been designed, but also in the kind of actually responsibilities that each of these so-called tiers has. The entry point is Cern, is a tier 0, records the data, reconstructs the data, and distributes the data. Then we have 13 sites around the world, which are called the tier 1 sites, which are responsible for storing another copy of the raw data, our primary data, and then they are responsible for the processing and the reconstruction and the analysis. And then we have 140 tier 2 sites, which are responsible for producing simulated data and also support the analysts for their end-user analysis. So basically, we have an infrastructure which is never sleeping, the grid. And it is located almost everywhere. We have 42 countries, so a little bit more also than those participating into the World Cup. And they're coming from basically all continents except Antarctica. We are working hard on that. And in numbers, just to give you a feeling of what we're talking about when we're talking about the grid, I would like to emphasize a couple of points. We have today about 1 million CPU cores that are available to scientists. We have about 1 exabyte of storage, so we are in the era of exabytes. We have about 2 million jobs, we call them, is pipelines that run on the grid every day. And we have these 170 centers that need to be connected via networks. I'm displaying here the one that is just between the tier 0 and the tier 1s. We have links of about, capabilities of about 10 to 100 gigabit per second. And of course, the transatlantic link is more important. It's got a capability of about 340 gigabit per second. With this network, we move an impressive amount of data, impressive at least to us. We move something like 3 petabytes of data every day. So we are certainly leaders in distribution and in data management. And actually, I wanted to spend a second also in telling you about the data management problem at the WSCG. Is an important and key area of development. You can see on the left-hand side the kind of distribution and transfers that we make. This is just a screenshot from a day, and you can see the transatlantic transfers. It's really something that we do, makes our environment rather unique. Not many other sciences do this so much nowadays. So to be prepared for the future when we will have more data, when we will have bigger data sets, we are actually in the process of redesigning the way we want to handle data management for the future. We have 170 sites. We would like to go for 2 key, let's say, elements. One is consolidation of the storage infrastructures, possibly making some of these 170 sites logically connected and sharing operations of the storage infrastructure in order to save on cost, not only for operations, but also for data replication, which is an important factor of the way we spend storage resources nowadays on the grid. Another key element is how we want to serve the data, not only to our sites that are on the grid, but in particular to those external centers which offer us great opportunities for additional resources, such as the commercial clouds and the HPC centers. And I'm going to get back to this in a moment again. So moving to the program of the upgrades of the LHC, I would like to give some more detail about what comes in the future. And I'm starting with the time scale, actually, of the entire program. The LHC, from the start, has been designed in order to follow a carefully set out program of upgrades. You can see this in this schedule. You have actually periods of run, which are interspaced with the periods of long shutdowns. So a run is typically 3 years, and then we have 2 years in order to make changes. The second, the run 2, started when I was, in fact, coordinator in 2015, and is going to end at the end of 2018. And then we will have, again, an opportunity of 2 years, the long shutdown 2, in order to make changes. We will restart in 2021 with run 3, which we see the upgrade of 2 of the 4 experiments. The LHCb experiment and ALICE will upgrade basically in the next couple of years. So there is a lot that is being done in order to prepare for this upgrade. We will have again 3 years running, and then we will have a longer shutdown. The long shutdown 3 is longer because not only some of the other 2 experiments will be upgraded, but also the machine will be upgraded. And will be upgraded, you can see here the curve of these red dots. This is the instantaneous luminosity, the nominal luminosity that gives a way to basically is proportional to the number of collisions that happen in a given time. So going higher in luminosity and plateauing here is going to give us, with respect to what we do today, much more collisions, much more data that we need to analyze, but also much more statistics in order to be more sensitive to new physics. And this is, of course, very important because we want to have a machine that actually greatly has the opportunity of increasing the scientific reach. So the program, which is starting with an upgrade and going up of the instantaneous luminosity from run 4 to run 6, is called a high luminosity LHC. Why do we need more statistics? Because what we observe is incredibly rare. And out of for instance, in order to have the sensitivity to observe new physics, we need to produce for one event potentially symbolizing new physics, say the Higgs boson, 10 trillion events are generated at the LHC. So we have an important data mining problem here that we need to tackle basically every day in order to make possible to look for new physics or to do precise measurements. So it is very important to upgrade the machine because of that. And just to give you a feeling of what it means, to look for one particular event over 10 trillions is like you want to find that particular grain of sand over 20 volleyball courts, which is quite impressive, actually, and tells you how smart we have to do some of our things in high energy physics, and in particular at the LHC. Now, I find another impressive component of all this is actually coming from the way in which the events are produced at the LHC. When we are filtering on one event, we need to read out a number of simultaneous other collisions which are happening at the same time in the beam pipe. And today, at run 2, we are handling something like 50 simultaneous events. Sometimes it's a bit more. This is a record event from CMS experiment last year with 7 and 8 simultaneous reconstructed vertices that we need all to disentangle in order to understand that event that we have been filtering on. And this average, we call this pile-up, this average pile-up events of 50, which we have nowadays on run 2, can be compared with what we had at the beginning. The machine at the beginning had the lower luminosity, so we had the lower pile-up, about 15 was what we were handling in run 1. But what we are expecting for the high luminosity of LHC is actually the purple tracks. So we will be triggering onto one event, but we will have to disentangle it out of 200 simultaneously that will happen at the same time. And this is why reconstruction is actually a very complex problem also for the future. During run 3, I already mentioned it when we looked at the schedule. We will have an upgrade for 2 of the 4 experiments, LHCb and ALICE. They will increase greatly their data acceptance rates exactly in order to be able to do more physics. But this brings in a couple of problems. The first problem is that we won't have enough resources to process data later on during the year as we do today offline. But everything will have to come and be there and be done basically in real time. As soon as data is collected, they will have to be reconstructed, and data analysis will have to be performed. And this is a major change with respect to what we do today. And we have to use new technologies in order to be able to do that. And you will see in a moment also why. I wanted also to mention that because we are going for an upgrade, and because the two experiments will have to handle more data, then their high-level filter farms are going to be upgraded as well. And this is actually, this schematics gives you an idea of the kind of upgrades that the two experiments have been planning on in terms of container data centers. By run 4, the other two experiments will be upgraded. And this is a view of one of the detectors which are going to be built in the CMS experiment. Because we have more occupancy in the detectors, we need to build detectors that are more granular. And this is why we have these 3 years in which the machine will be changed, but also the experiments will be upgraded, including the detectors. And this is one of the major areas of work that is currently ongoing into the experiments. The occupancy is impressive. You can see it in this plot, at least it looks impressive to me. And the capabilities that will come with these detectors will be able, the granularity will be able to disentangle each of these dots that you see, which are actually tracks which are deposited into the calorimeters, which measure the energy of the particles. So reconstructing more particles with more granular detectors will be computationally much more expensive. And a way to see what we need in terms of resources is given by this distribution delivered by the Atlas experiment. Is a forecast of what is needed compared to what we have today in terms of CPU and in terms of storage. The blue dots represent what the experiment needs. You can compare what we have today in 2018 to what we will need at the down the line, for instance, in 2026, where we will operating the machine in the regime of the high luminosity LHC. And if you count here, we are ended up with a factor 50 to 100 times more than what we have and we use today. And this is an impressive amount of resources that are demanded, especially when you have to deal with a flat budget. The curve, which is the black curve, which is displayed, is the technology evolution which is expected between now and when the LHC, the high luminosity LHC will be running. Within the so-called flat budget, that is what we have. And you can see, therefore, that some of this gap will be taken care of by the technology evolution, so by your work, and we will be left with something like a factor 4 for what concerns the need of additional CPU, so computing, and a factor 8 with respect to what we need in terms of storage. And you can also see here by these predictions that we will basically enter the scale in which each experiment is producing exascales of data and not anymore the 50 petabytes of data per year that we have today. So it's a huge, huge need for the future, which is represented by these factors 4 to 8. Is not a small path, the one that we have for the future. A way to visualize this is given by this pie chart that I'm just showing. So closing the resource gap in the next decade is the problem that we need to face. And I would say that a third is going to come from improvements in hardware, performance and capacity, so by industry. But quite a significant fraction of this, 2/3 of this, has to come from new ways of doing things, so from innovation and revolutionary thinking, and we hope to be able to count on the collaboration with industry in order to do this together. So my job currently is actually to make possible that there is industry collaboration with researchers at Cern. So my next slide is summarizing the framework of collaboration that exists at Cern since 17 years in order to work together with the industry. It's called the Cern openlab. Has been there for 17 years, created for the support of the LHC program and its challenges in computing and software. You can see here the technology leaders that we have as members of openlab, together with the research members. And of course, the focus of what we do is fostering innovation and research, be able to perform joint research and development projects together, and expose technologies in quite challenging environments, such as those that Cern can give. Another important part of what we do in openlab is actually towards innovation, so looking at technologies that might come in the future or might come in the future, it will depend. And also knowledge transfer. And we also have a solid program of education and training for young scientists through dedicated students' projects that we typically run in summer. And we also have an important role for the dissemination of the technologies that we study together with industry and the kind of results that we get in those joint projects that we do with these leaders in technology. Of course, the goal that we have for the next 3 years and the years to come is to support the upgrade programs and the computing challenges behind them. So we just started the so-called phase 6 of Cern openlab, and the areas where we are going to concentrate for the future are, on one side, data center technologies and infrastructures with the exploration of new architectures, but at the same time studying how to scale out capacity with the public clouds and HPC. On the other side, data center performance with the hardware accelerators and optimized software. And the last part is exploring new techniques that will be enabling us in order to have these components of innovation and revolutionary thinking that I was telling will help us to close the gap. So some examples of what we are doing in data center technologies are coming in a moment. When we are faced with a resource gap of this magnitude, said factor 4 to 10, let's say, there are 2 areas of investigation. One is to be able to fully exploit the available hardware, and the other one is to expand dynamically to new computing environments. And I'm going to have a couple of slides on each of those, complementary, and the 2 of them very important too. So the first step to be fully exploiting the available hardware is actually coming from using the resources via virtualized and layer services. This is what Cern has adopted. OpenStack has been one of the early adopters and one of the largest contributors to OpenStack. We have virtualized all our resources, and we have something like more than 90% of resources which are provided through a public cloud. At the same time, this allows us, the virtualization and the layering of the services allows us to be flexible and dynamic. And we're also, therefore, looking also, for containers within what we do in Cern openlab with industry to even achieve more flexibility. Scaling out to additional resources is something that we've been worrying since a couple of years. I've been involved when I was CMS coordinator into a couple of large-scale investigations with commercial cloud providers, and this is the result of the investigations performed by the CMS experiment in collaboration with Fermilab, with Amazon Web Services, and with the Google Cloud. We have been reaching impressive scale-out tests where we have been doubling our resources for performing reconstruction of data on one side with Amazon Web Services, and on the other side with Google simulation, reaching to something like 300,000 cores, which is more than doubling the amount of resources that we have in an experiment today at the LHC. Similar tests have been carried out also by Atlas, but with similar results. Another area of work in cloud services that I would like to bring up today is the project, which is a EU Horizon 2020 project, Helix Nebula Science Cloud. The interest here is that it is a joint procurement of innovative cloud services together with other research collaborations. There are a total of 7 sciences that are involved in this project, and the results will be an hybrid cloud which is combining the data centers from the procurers, the commercial cloud services from the providers, the giant network, and the GAIN network for identity management. Moving now to the investigations that we do in the sector of HPC, I would like to show some very recent and impressive results which have been obtained by the Atlas collaboration using HPC resources in United States. They've been reaching an impressive scale of 200,000 cores of traditional x86 HPC cores, which have been used in order to produce simulation data samples. And you can see here in the plots the comparison with respect to what the experiment typically has. So really scaling out for more than double than the normal cores that they have is very, very good results. At the same time, experiments are also exploring the use of additional capabilities which are offered by the HPC, which are the heterogeneous HPC architectures, and there's been ongoing work by basically all experiments, and I'm going to show a couple of results later. Studies will also partner with PRAISE, in fact, for helping exactly in this area of HPC for optimizing the use of resources and help the experiments in order to be fully equipped for the best use that we can have of HPCs, which of course are a significant resource for our environment. So it's very important to be able to scale out to those resources in an efficient way. A very interesting and innovative approach to HPC has been taken by Deepest. I would like to mention this project also supported by the European community. I'm personally involved in it. It's an innovative blueprint project for heterogeneous and modular HPC systems. The modules in Deepest will have specific capabilities from traditional HPC to a booster and accelerator component and module to a fully dedicated